see this problem. There are 3 questions in this problem. First of all, I will discuss the first one. A magnetic field that varies in magnitude from point to point but has a constant direction east to west is set up in a chamber. A charged particle enters the chamber and travels undeflected along a straight path with a constant speed. What can you say about the initial velocity of the particle? So our motive is there is a magnetic field which varies in magnitude. So in that sense, in this case, at this point the magnetic field is more. At this point magnetic field is more, but here it is less. So according to the given thing, so it varies from point to point. Here it is more, here it is less, here it is more. So in this field a charged particle is moving. So we don't know the direction. First of all, a charged particle is moving, but it is moving without deflection. So we need to find out the nature of the velocity of that particle. Now come to investigation part. So the charged particle has some velocity, there is a field, and it has charge. Now come to the resolving part. We know that the force experienced by a charged particle under some magnetic field is written as F is equal to Q into V cross B. So in this case, if the charge is not experiencing any force, even though it has charge, even though the field is there, even though it has some velocity, it is not experiencing any force. So that means force is 0, which can be equal to QVB sine theta. So here Q is not 0, V is not 0, and B is not 0. What should be 0? Sine theta. Then sine theta is equal to 0. This will be happen when theta is equal to 0 or 180 degrees. That means the direction of the charge is either parallel to the field or anti-parallel to the field, so that the angle between those two directions is 0 or 180. So either parallel to the field or anti-parallel to the field, it won't experience any force and it will move without any deflection. So here the direction of the velocity of this charged particle is either parallel or anti-parallel to the field direction. In second problem, a charged particle enters an environment of a strong and a non-uniform magnetic field varying from point to point both in magnitude and direction, and comes out of it following a complicated trajectory. Would its final speed equal to the initial speed of it suffered no collision with the environment? So come to the motive. Here the field is non-uniform and it is varying in magnitude and even in direction also. In earlier case only the magnitude is changing, not the direction, but here even direction also changing. So I can guess the field like, so when you consider here the magnetic field value is less and here also less, but here it is more. If you consider the direction of the magnetic field, here it is in this direction and here it is in this direction, and here also it is in this direction. It is not maintaining a constant direction and constant magnitude also, it is varying. So I can guess the magnetic field like this. In this field some charge is moving, so we need to find out the nature of the speed of the charge. So in the problem it is given that it is coming with a complicated trajectory. So because of this varying field, it can make some different type of trajectory, and we need to comment about the speed of this charged particle. That is our motive. Now come to the investigation part. Here I want to explain one mechanical concept. I have a ball, so I am applying a force on it, so it will attain some velocity. So when I am applying a force, the ball is moving in the force direction and it is changing its kinetic energy. So there must be a work done. Now I am rotating this ball by hanging with the thread in a circular motion. Here the direction of the force applied on the object is perpendicular to the motion of the object. Here work done is equal to 0. So when work done is equal to 0, there is no change in kinetic energy. So that means the particle will move in other direction and as well as with uniform speed. It won't be accelerated in the direction of the motion, but it will be accelerated towards the center of the motion. At this moment, the speed will not change, but the velocity will change continuously. When work done is 0, or when the change in kinetic energy is 0 in a moving object, then we can say that the speed attained by that object is constant. Now come to the resolving part for this example. We all know about Fleming's left hand rule. If you stretch your left hand's thumb, forefinger and middle finger into 3 mutually perpendicular directions, then your middle finger shows the direction of the current and your forefinger shows the magnetic field applied on that current object, and current object experienced by a force which is perpendicular to these two directions. And this is the direction which is shown by the thumb. Here the force experienced by the current element is perpendicular to the direction of the current, and even if it is not maintaining the perpendicular field, like for example a charge is moving in the field which is making some angle theta with the field, then at that moment also the force experienced by this charged object will be perpendicular to the plane containing this B and I. So at that moment also the force direction is perpendicular to the current's direction. That means whenever a magnetic field is applied on the charge which is moving in a region, the force experienced by the charge will always be perpendicular to the motion of the charge. So the same concept I can use it here also. So here when the force is perpendicular to the motion of the object, the work done on the object is 0, and here also the force experienced by the charged particle is always perpendicular to the direction of the current. Then in this case the work done is 0, then the change in kinetic energy of the charged particle is also 0. That means the speed of the charged particle is constant, but the velocity will continuously changes. That means the direction of the charged particle will change continuously due to this varying field. In the third problem, an electron traveling west to east enters a chamber having a uniform electrostatic field in north to south direction. Specify the direction in which a uniform magnetic field should be set up to prevent the electron from deflecting from its straight line path. Our motive is, so an electron is moving in one direction, so it has entered into a chamber where the electric field exists from north to south, and the electron is moving from west to east. So when a field set into north to south, we can assume two parallel plates which are looking like this, and here the field is from north to south, that is from positive to negative plate. So due to this electric field, the electron will be attracted towards the positive plate, so it will deviate like this. So electric force Fe is attracting this electron towards the positive plate. To make it undeflected, we need to apply a counter force towards the south direction using magnetic field. So we can write it as Fp. So our motive is, we need to apply a magnetic field such that the magnetic force due to that magnetic field on the electron will counter this electrostatic force. Now come to the investigation part. We all know about Fleming's left hand rule. While resolving, the electron is moving from west to east. That means the current direction is towards west, and you are expecting a force which is towards the south. So we need to apply a magnetic field perpendicular to these two directions, either out of the plane or into the plane. So using Fleming's left hand rule, we can easily assess this. The magnetic field should apply on this electron should be inward. So this is wrong. This is the magnetic field direction should apply, that means inwards. This is the representation of inward direction, and the dot circle is the outward direction representation. And here if you apply a magnetic field inward, then the electron will experience counter force so that it won't deviate from its path. So in this case, so electron is moving from west to east, and electrostatic force is acting towards north, and you are expecting magnetic force towards south. So here we need to apply the magnetic field downwards. Due to this magnetic field which is acting downwards, a counter magnetic force will oppose the electrostatic force such that that electron will not deviate from its path.